The James Webb Space Telescope, our newest and most observant tool for studying the expanding universe, is revealing previously unknown phenomena. James Webb is expanding our understanding of the 400 million years after the Big Bang, as well as providing insight into the possible existence of extraterrestrial life by studying phenomena such as the deposition of sand on other planets and distant galaxies. But note that James Webb not only obtained amazing infrared photos, but also made new discoveries that challenge the Big Bang theory and challenge some truths that we thought were established. The Big Bang was an exciting event. However, it did not mark the beginning of all existence. James Webb's recent discovery has caused a stir in the scientific community. This can challenge the current standard model of the evolution of the universe and even contradict one of the fundamental laws of physics. In particular, the discovery suggests that the Big Bang theory may be wrong and that the universe may be larger and older than previously thought. This revelation has great significance. When we look at our cosmos today, we not only see a wide variety of stars and galaxies both near and far, but we also see a fascinating relationship. The farther away a galaxy is, the faster it is moving away from us. This phenomenon persists within the current range of observations and applies to all galaxies. The further away they are, the stronger their measured redshift, indicating their recession in cosmic terms. The universe is expanding, causing galaxies and clusters of galaxies to gradually recede from each other. Thus, space in earlier times had a higher temperature, a higher density, and all its components were closer together. Consider the consequences of the continued expansion of the universe, both now and throughout its cosmic history. Extrapolating very far, we arrive at a time before the first galaxies formed, before the first stars ignited, and before neutral atoms, nuclei, or stable matter existed. The earliest point at which we can describe our universe as hot, dense, and uniformly filled with matter is called the Big Bang. The last sentence might be difficult for some of you to understand. One might ask, isn't the Big Bang the creation of time and space? This is a position with which many modern cosmologists can sympathize. At one point in the history of cosmology, the Big Bang was originally thought of like this. Take something that's expanding and is a certain size and age today, and you can go back to a time when it was arbitrarily small and dense. A single point where all the matter and energy of the universe come together at once. This event corresponds to what we know as the singularity, the point from which space and time first appeared. But we know that is not right today. In fact, in 2023, there is plenty of evidence to suggest a non-singular origin for our universe. We never got these arbitrarily high temperatures. There is an interruption. Instead, our universe is best defined by the inflationary phase that occurred before the Big Bang, and the Big Bang is the result of what happened at the end of inflation. Let's go through what it looked like. During inflation, the universe was completely empty. No particles, no matter, no photons, just empty space itself. Each point in that void contained an enormous amount of energy, and the exact amount of energy varied greatly over time, averaging about 1 part in 30,000. As the universe fills and expands rapidly, continuously, these fluctuations become larger, while new small-scale fluctuations are created on top of them. This superimposition of fluctuations on small scales over mesoscales on the large superhorizon scale is one of the predicted characteristics of cosmic inflation. This will last as long as inflation lasts. However, inflation ends randomly and not in all areas at once. In fact, if you lived in an expanding universe, you would probably end up in a local place where inflation would end, because the space between you and it has expanded so much. You might even briefly see what happens when the Big Bang starts, before the area completely disappears from view. Initially, over a relatively small area, perhaps no larger than a human-sized hamster ball, but perhaps much larger, space energy is transformed into matter and radiation. The conversion process is relatively fast, takes about 10 to minus 33 seconds, a short time, but not instant. As the energy locked in space itself transforms into particles, antiparticles, photons, and more, the temperature begins to rapidly rise from a few degrees above absolute zero to roughly 10 degrees to 20 Kelvin in the same small amount of time. Because the amount of energy converted is so great, everything moves close to the speed of light. All particles behave like radiation with such high kinetic energy, regardless of whether they are massless or massive. Under these conditions, this conversion process is called rewarming, and it means that inflation stops and the phase known as the hot Big Bang begins. As for the expansion rate, you will notice a dramatic difference from the previous behavior at the start of the hot Big Bang. In an inflationary universe, space is expanding explosively and distant places are constantly drifting away. But when inflation ends, the universe heats up and the hot Big Bang begins. Distant areas now move away from you more and more slowly over time. From the outside, the part of the universe where inflation ends will experience a reduction in its rate of expansion, while the surrounding expanding regions will see no such decline. During inflation, the distance to something doubles after a certain amount of time, and when the same amount of time passes, the distance doubles again and again and again. The process is continuous, but after the Big Bang, everything changes when the expanding cosmos suddenly slows down. After the first moment of expansion has passed, it is quite likely that for any pre-Big Bang space expansion sector, you will experience the end of inflation many times in the surrounding areas. Those places where inflation ends quickly fill up with matter, antimatter, and radiation and expand more slowly than the regions that are still filling up, leaving you with a region of space-time that dominates its volume. Those Big Bang hotspots extend away from all the other places where inflation continues exponentially, meaning they are rapidly receding from each other's vision. In the classic inflationary picture, because of this change in the speed of expansion, there is almost a small chance that any two worlds of different hot big explosions could ever meet or interact. Eventually, the area we live in will be cosmically lucky and inflation will stop. The energy contained in space becomes a hot, dense, and almost uniform sea of particles. The only errors and deviations from unity are related to the quantum fluctuations that existed during inflation and spread throughout the universe. Quantum fluctuations of positive energy correlate to initially overdense regions, while negative energy fluctuations correlate to initially everdense regions. Normal variability can be as low as 0.003%, but that is enough to be possible seeds of cosmic structure. We cannot witness these density fluctuations today, as they were when the cosmos first experienced the hot Big Bang. There are no visual cues we can use from this early time. The first we ever get to is 380,000 years later, after they have endured countless exchanges. Even at this point, we can extrapolate back to the initial density fluctuations and find something very consistent with the story of cosmic inflation. Temperature fluctuations captured in the first image of the universe, the cosmic microwave background, give us information about the beginning of the Big Bang. However, we can sometimes detect gravitational waves left over from the end of inflation and the start of the hot Big Bang. These gravitational waves travel in all directions at the speed of light, but unlike optical signatures, no interaction ever slows them down. They flood us, constantly arriving from all directions, flowing through our bodies and detectors. All we have to do if we want to understand how our universe began is to find a way to observe these waves, either directly or indirectly. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss a future episode.